Repeat, today's session we'll do a topic called multilinear regression. What is it? Right. What are factors that affect it? We'll talk about something called multi-collinearity. Multi-collinearity in your book is just called collinearity. It is the same thing. We will talk about outliers and leverage points. And we are going to do all of this from a very practical perspective through lab examples at some point. So we are going to talk about all of these things. We are also going to talk about something, we talked about the Gauss-Markov theorem, Gauss-Markov theorem, and assumptions. And again, we'll do it from a very practical data. This, and that will finish our world with regression. Today is the last day for regression. We would be done with it after doing some labs. Quite likely this will eat up most of our time. We will do a quiz, in-class quiz that each of you will get online after this regression. And then, time permitting, we'll start the new topic of classification. Right, guys. Now, one thing I wanted to ask, I've released the solutions to all of this exploratory data analysis. Does anybody have any questions on that? Do you guys feel that I should walk over the solution or it is unnecessary? I will go with the assumption that it is unnecessary, but if you folks feel that it is needed, what I will do is give an extra session, let's say Wednesday evening or something like that, in which I'll just walk over the solutions. Will that be something you guys would be interested in? Last time I offered an extra session, nobody showed up. So if you're interested, drop me a word if you are. Based on how many people are interested, we'll do a walkthrough session of the exploratory data analysis. There I might talk about more tips and tricks from real life experience. So that would be our scope.
Yeah, Wednesday will work.
Sure, yeah.
Sure, sounds good.
Yeah. So we'll go with that. So, when I talked about, I'll start with this thing. I talked about Gauss-Markov theorem, and I said that in one dimension, it just comes back to the simple statement. The line should be essentially going through the center of the data, and the data point should be scattered more or less around the line uniformly. The important word was uniformly. Now, when you go to multilinear or many predictors, what does multilinear mean? Many predictors, when they come in, let's write it out. First topic, multilinear regression. Regression. What does it mean? Let's go to the example of our sale of ice cream on the beach. Ice cream. How much ice cream are you selling? This is our Y. Right? And let's just say that we have two axes now. One of them was temperature. Remember, this was an X1 now. And suppose you have another factor, which is how windy it is. Why would the wind matter on a beach? Well, let's make a narrative that if it is windy, it will the waves will be coming in pretty high, and it wouldn't be safe to take kids into the pool, right, into the water. So obviously, that is going to affect how many parents will show up with their kids on the beach, and so your sale of ice cream would be affected. So you would say that your ice cream sale depends upon, Y depends upon a beta naught plus, it will depend upon this being the temperature, and it will depend upon X, which will be wind. Winds. Does this look like a very natural generalization, guys? Guys, I'm getting a lot of static in the background, scratching sound.
Yeah.
Folks can please mute yourself if the scratching is coming from you. That will be good. Huh? So, all right. So far so good. Are we getting this, guys? It's a very simple generalization. But what does this equation represent? We realize that in one dimension, when there was only one predictor, it represented a line. A regression represented a line. But in two dimensions, what do you think the regression equation will represent? Can somebody guess it?
Plane.
Yes, it will represent a plane. Equation, geometrically, this is a plane. Is a plane. Right? And these are the partial slopes, like slopes in the x1 direction and x2 direction of the plane. So it will be some plane rising up from here. Oh, actually, it will be rising up rather. Let me use some other. It will be some plane rising up, which represents the relationship of y on x1, x2. So to be able to do this, you are writing your first multi-linear regression. People don't usually use the word multilinear regression unless they want to make the meaning clear. So rarely they use it. They still call it linear regression. Are we together? Now, this is your basic term of linear regression. Now, for this to work, everything remains the same. Your sum squared error, your gradient descent, everything remains the same. Why? Because our error term is simply y minus y hat I. If you remember, it is the sum of squared of mistakes. So suppose this is the prediction. Let me take this. You realize that at this given value of this point, which is x1, x2, what is the prediction? Let me use a more bright color. What is the prediction? The prediction is this, right? This is y hat. And what is the reality? Let's say that this is the reality. This is y. And therefore, what is the residue, the mistake? This is the error. All right. Does this make sense, guys? For any place, any value of x1, x2, which will be in the base plane, there will be a prediction, which is the point on the plane and the reality, and the residues remain the same. So in other words, all your theory of linear regression that you have learned so far applies. For multilinear regression, they just, when you have many, many variables, a few factors become important. And I'm going to mention those factors. In fact, those are the famous, the Gauss-Markov assumptions. So one assumption is very basic. It is the random assumption. Random assumption just says that your data, when you take the data, it should be a good random sample of reality. Means don't take data points such that they are skewed for whatever reason. They are all on the optimistic side, or they're all on the the lower bound side or something like that. Don't put bias in your data. Truly take a good random sample of the data. Are we together? The second condition of Gauss-Markov is linearity. It's common sense, which basically says that your equation should look like this. Whatever, right? I'm writing it for two variables. When I'm writing it for two variables, you can assume that it is for n variables. You can have more. Actually, p variables, let's say, xp. I'll follow the convention that is in the textbook. Huh? Linearity condition. Then there is another condition, which is common sense. Again, see, these are just common sense quantified, guys. Huh? Here, do you notice that all the points, all the errors are around the line? This the real data is around the line, which means that the residues are all small. And if you remember, we use the word that if you make a frequency of the residues are, or the errors are, residuals rather, they have a distribution like most of the errors. You can have errors close to zero, and then you're much more likely to have small errors and much less likely to have, this is the, this is just a, think of it that if you make a histogram, right? Think of it as a histogram of errors. It should basically look like a bell curve. So why should it look like a bell curve? Like what it shouldn't look like is like this. Suppose this is the zero. It shouldn't look like or some weird thing, because that wouldn't make sense. If you have a line in which all the data points is here, do you think this is a good representation of a reality? It wouldn't be. Why? Because all of them are skewed to one side. And sometimes what happens is you have yet another problem, which is that here, see if you can identify what I'm doing. I'm doing something very funny. And here, this looks like a line, but imagine it's a hyperplane. It's the plane. Oh, suppose data points are like this. Do you see something weird happening with this data? What will happen is, as y rises in this, you will realize that the residuals, they become bigger and bigger, right? Do you see that the residuals are becoming bigger and bigger? The residuals are spread out more and more. You see the envelope here.
That weird word.
The errors, these are the error boundaries, right? Where the data is sitting. So these are your residuals. And what you notice is that you have a cone. They will show a cone-like structure. Cone-like structure. When you see this, you don't want to see this because it violates Gauss-Markov assumption. The assumption is something called homoscedasticity. Oh boy, this is rather a big word. What does it mean? I keep telling people that if you are familiar with Mary Poppins, the story of Mary Poppins, there is a word which is really very big. And children are taught, and when they know that word, they feel pretty grand about themselves. I would say that when you start with machine learning, this word homoscedasticity and its opposite, heteroscedasticity, are words in that category. What homoscedasticity is, the errors, if you plot the errors, so by the way, I will now plot the errors in terms of y itself, and these residuals are there, residuals. What you will find is the residuals are like uniformly there. So if you sort of draw an envelope around them, they will be pretty uniform envelope. But heteroscedasticity is, if you look at the errors along the y-axis, if you do it, you will see this cone-like behavior. Sorry, I shouldn't do that. So guys, do you see the difference between these two? What is the difference? How would you say that word? So this is residuals. I'll just use the word errors, the error terms, errors. What can you say about the errors in the first situation on the left, the homoscedasticity versus the heteroscedasticity?
First term is constant, while the second term the error increases.
Yeah. It opens out like a cone geometrically, isn't it?
Yeah.
So what is a measure of spread? When you look at the spread of a variable, how do you measure it? See, if you look at this value, at any given value of y, right, the average would probably, the residuals will probably average out to 0. But what is different between this and this? What is different?
Standard deviation.
What's that?
The deviation increases.
Excellent. The standard deviation or the square of standard deviation, which we call sigma square. Sigma square of error is constant. Isn't it, guys? More or less. Whereas what about this? Sigma square of error, sigma square, or people just write it as a variance, the same thing as variance. Variance of the error is proportional to y. It depends on y, the response, isn't it, guys? Do you see that? As y increases, the variance becomes bigger. So for example, let me call it sigma 1 square, sigma 2 square, sigma 3 square at the third point, and this is y1, y2, y3. So what can you say about the sigma 1? If you were to compare sigma 1, sigma 2, sigma 3, what will you see? Sigma 3 square will be greater, and of course sigma also, will be greater than sigma 2 square, will be greater than, would it be something like this, guys? That as you increase y, the sigma square keeps on increasing. And you know, the cone could have been in the other direction. It doesn't matter. In this case, it seems to increase with y, or it could have been decreasing with y. The fundamental thing is that it is related to the target variable itself, the variance of the error. Whereas what can you say here? Here, if I take 3 points, 1, 2, 3 in the y-axis, would you be able to say that sigma 1 square of the error is approximately sigma 2 square is approximately sigma 3 square? Does this make sense, guys? Anybody would want me to explain it again? This is a very important concept. And the reason I'm mentioning it is most books that talk of machine learning actually miss that. Miss the fact that linear regression does not work unless your model is proven to, to have homoscedasticity. You have to check after building your model. And if you don't check, well, there is a better model that can be built, right? And in fact, you're in violation of the Gauss-Markov assumptions, right? So they are randomness of the data, linearity, the error residuals must be in a bell curve. So this is called the normality of it. Normality of errors. Why normal? Like, what is abnormal otherwise? The word normal in mathematics stands for the bell curve. It's a very interesting thing. Whenever you hear the word the normal distribution, it doesn't mean normal in the general sense. It means the bell curve or the Gaussian distribution. And then, so the errors must have a Gaussian distribution. And more than that, the variance of the error should not change. The spread of the error shouldn't change as you change the value of y. It shouldn't depend on that. So these are the fundamental, I think did I capture all of them? Randomness, linearity, residuals, homoscedasticity. I get the feeling I'm missing out on one more. Can somebody tell me what did I miss out on?
Multi-collinearity, I think.
Oh, multi-collinearity, of course, the thing that I was going to talk about. Yes, thank you. Multi-collinearity. So blue, multi-collinearity. So what is multicollinearity? If it is present, should not have multicollinearity. Now, multicollinearity is something that needs to be understood. So I'll write the equation again. Y depends on beta naught plus beta 1 x1 plus beta 2 x2. And guys, we'll do a lot of code walkthroughs in practical data. So you will see what all of these things mean. So see, you expect y and x to be related, right? So for example, a good to have would be correlation between x1y, x2y. Those are good things, isn't it? But what is a bad thing is bad if x2 is very has a close correlation, is correlated, strongly correlated to x1. Can you guess why that is a bad thing? Or why, what will two variables in a model that are highly correlated, what does it mean for two predictors to be highly correlated?
They move together.
They move together, isn't it? So for example, I'll give you an example. Suppose you use two instruments, one to measure the temperature in Celsius and one to measure the temperature in Fahrenheit. Right? So up to some small errors, instrumentation errors, what will be the, do you think that we need both of those readings to predict the sale of ice cream on the beach? Right? Would you rather that we wrote an equation like this? Y is this good? Beta naught, plus let's say 1 for beta 1. This is the wind speed, plus a beta 2, x2, which is temperature in degree Fahrenheit, and temperature in degree Fahrenheit. And this, suppose somebody has given you data like this. Temperature in degree Celsius, or let's say the degree Kelvin, or yeah, Celsius, let's say. The European versus the imperial standard, the metric versus the imperial standard of notation. Now, just common sense wise, what would you say if for a model like this?
I said there is redundancy here.
Exactly, there is redundancy because
What I don't understand is why it's a problem. Because like x2 and x3 can combine itself, and there's a beta 2, 3. Some new beta will come up.
Yes. Yeah. I'll explain. That's exactly what I'll explain. So let us say that x3 is approximately lambda times x2, isn't it? Highly collinear means if there's a very strong correlation means one can be represented in terms of the other, which is true, right? For example, x3, what is the relationship of x3? Temperature in Fahrenheit is, in centigrade is 5/9 over x2 minus 32. This is the relationship, isn't it?
Sure.
Yeah. Up to some error, some error term, because you'll have some instrumentation error. So what would it mean? If you look at the correlation, and people often use the word, this peculiar symbol. Do you see me writing a P? Right? But it's a very funny P. It is called rho. It is actually a Greek symbol. Greek symbol is the symbol for correlation. So let me just introduce that. It means the Pearson correlation. So this would be, let us say 95%, or 90, something like 95%. So you realize when two variables are highly correlated, you don't need both of them. Quite likely one is enough. Are we getting the point, guys? Because if one increases, the other will increase. And so why do I need to keep both of these variables? So now comes the question then, what is the harm in keeping it? And therein is a problem. So this problem, the fact when this is true, this is called collinearity. Or your book calls collinearity. The more general term is multi-collinearity. So first of all, guys, do we understand the meaning of collinearity or multi-collinearity? Would somebody like to rephrase it for me? What does it mean for you to have amongst the predictors, like for example, the inputs to are telling what is the sale of ice cream on a beach, two predictors, they exhibit multi-collinearity. What does that mean?
One is a linear transformation of the other.
Yeah, one is a linear. And that happens when they are strongly correlated. Strongly correlated will be that, remember, strong correlation would be that the relationship would be something like this between x3, x2, isn't it? Which is what it is between temperature in Celsius and Fahrenheit. So that is the multicollinearity. Is it a good thing or a bad? It turns out that multicollinearity gets the simpler machine learning models into a whole deal of trouble. In particular, linear models don't work well. And remember, this is true only for the linear models. You have to look at the situation on a case-by-case basis. But in general, linear models like linear regression, and we'll learn about classification, the logistic regression, and so forth, they sort of hate multicollinearity in the data. Your model will not function well. Why will the model not function well? The answer to that is quite geometric, actually. And I would like to give you an idea, but this explanation we will talk about later also. But I would like to finish it today with this explanation. So remember, we have the error surface, right? Let me call this beta 1 and beta 2. Why is this so fat? This is it. And this is the error surface. Do you guys remember what did we talk about? The error surface looks like a bowl with the best solution sitting here where it achieves the minima. Remember, guys, that the error, the sum squared error, achieves a minima at some point that we considered a solution. The best fit line, the best fit surface, and so forth. Now, something very funny happens. Imagine that you're looking at a bowl or a plastic cup, which is shaped like a bowl. And then, as kids do, you start squeezing that plastic cup so that instead of being round, and so let's look at the projection of this on the ground. You notice that this looks sort of concentric circles, right? These are what? The projections of these points on the ground, right? These contour lines. Something very interesting happens. When you have multicollinearity in the data, actually, let me make it just next to it. What will happen is, I should use green here. When you have multicollinearity of the data, the best solution that is there, around it, these ellipses become, these contour lines become, maybe I should have used white just to be, sorry, I want to stay with the same convention. Now, guys, when you look at this and you can imagine the error surface rising up from it, what can you tell about the error surface? It is in one direction. You notice that in perpendicular direction, it is very, very squished. Are we together?
If I see what is happening, it's beta 1, beta 2 are moving so close to each other, they are almost equal. When they are equal, the error is 0.
Not really. What happens is, see here, right? This is your beta 1, this is your beta 2. Your solution becomes a bit hard to find because this bowl it begins to look like a canyon. See, ideally, you would want the bowl from every side to look like this, isn't it? Whichever side you look at this bowl, it looks like this. But this bowl, the way it looks is, in one direction, it will look like this. Are we together? And in another direction, weirdly enough, you know what it will look like? It will just look like a flat canyon. Means on the other direction, it just looks like open, completely open. So imagine a bowl that you squeeze from the side, and this is where I wish we were in the classroom, I would have shown. Imagine a plastic bowl, or a bowl made out of silly putty. Take a nice symmetric ball and start squeezing it. What does it begin to look like? Very narrow. You get a nice canyon in the center, isn't it? It sort of becomes to look like this. Through this surface, do you see this? It gets squished. So here, there are so many places that look as though they are the minima.
Ashraf, you can show it through your video, like if you want, like.
Oh, the video. No, actually, that is. I don't have that bowl with me, so I can't show.
Oh, okay, okay.
I wish I had that. Okay, so keep this as an item, guys. At some point, I will create a. I'll create a video just to demonstrate what it does. But basically, the problem that it creates is at the bottom, yeah, you have a big flat region. So when you have a big flat region, now which of these points is the best solution? You know, it is like ending up in the Yosemite Valley, right, from the hills. Imagine your error surface looking like the Yosemite Valley and the Yosemite River is flowing. Well, you know what? Every point looks like the minima, isn't it? And so your solution becomes very unstable. Based on your data, whatever data you have, it will randomly pick. Sometimes this point will get picked. Sometimes this point will get picked. So what happens is very small changes in data will lead to vastly different solutions. So I will write that down. Very small changes, data sample. So you take a different sample of the data, solution changes. Greatly. Are we together? And it changes very drastically, actually, and we'll see that in the next few labs. What happens is, suppose you have x2 and x3, sometimes your model will say x2 matters and x3 doesn't matter. And sometimes it will say x3 matters and x2 doesn't matter. So in other words, Fahrenheit temperature in Fahrenheit matters, but Celsius doesn't matter. And sometimes it will say Celsius matters, but Fahrenheit doesn't matter. Right? So this is it. Another way of putting it is, another observation that you'll get is between two x2, x3, which are correlated, highly correlated. Sometimes, so well, sometimes only one factor will look important and the other won't look important, and other will look unimportant. Important. And you change the data just a little bit and it will flip over. Small changes. Flips the solution. So this is a problem with linear, and remember this is limited to linear regression models. Or basic, what people will call the standard linear regression models, the way we have written. I think your book uses the word standard, and this is actually pointed out by a TA in our class. As the book calls it, standard linear regression. But generally, linear regression models, which have this particular property, if they exhibit collinearity in the data, the model is up for a toss. Right? So just to summarize, and this is very important, people blindly use linear regression models because it's something that everybody sort of knows or learns in the beginning of machine learning. So the basic assumptions are randomness, data must be random, equation must be linear, normality of errors, normal equation. And what else did we have? Collinearity. absent. And what is the other thing? Between homoscedasticity and heteroscedasticity, which one do you want? Let's go up and see. Between homoscedasticity,
Homo.
homo, right? We want this situation to be there. So this situation is in the data. What we say is that homoscedasity. So these are called the Gauss-Markov assumptions. Isn't it surprising? This whole thing was worked out already by about 1816 or 1812. Isn't it surprising that it's so long ago? All of these things were well understood and proven. It's a theorem, actually. And so if all these assumptions are met, then your sum squared error term being just this, y minus y hat, I, right, will be, and minimizing this would be the best way to approach the problem. That was the blue theorem. That Gauss-Markov theorem says that if all the conditions are met, then all you need to do is take the square of it. Remember, I put this in context by saying, why not take the absolute value? Why not take a lot of other terms to it, and so on and so forth, so that it is a theorem. Now, are these always obeyed? It turns out that they don't have to be obeyed. When they are not obeyed, you need to make more sophisticated models. Right? All is not lost. But you can't be using just the straightforward linear regression models. So we will talk about that today. So for example, if one very simple generalization we talked about, you can generalize it to polynomials, right? Beta naught plus beta 1 x squared. Suppose it is in single dimension plus x2 x squared plus and so forth. This is the polynomial expansion. We did that for one dimension, and the same thing applies to multiple dimensions. You can go to higher dimensions. The other thing you can do is you can say, well, in the case of multi-dimensions, you can have other terms that is like that. x1 plus beta 2 x2. Now let me bring something strange here. x1, x2. Now, what is this? This is strange. You notice that it doesn't depend on either x directly on x1 or x2, but on the product of the two. So when will this be true? I'll give you an example. Suppose you are looking for the price of a house, the value of a house in a certain neighborhood, all other factors being the same, the school district being the same, right? And the crime in that neighborhood being exactly.
Hello, my son.
Then the
You
price.
still have a desk, you know.
Oh, Kate, we can hear you.
Oh.
So, given a neighborhood in which there are many houses, and the school district is the same, the crime rate is the same, people's income are more or less within a narrow band. The house price, suppose you measure, and a very simple example, you measure house prices. And what you get is, suppose this is a house, I'll contrive an example. You get the length of the house, length, you get the width of the house, and you get, let's say, how many floors it has. Floors. Let me call this x1, x2, x3, right? So when you look at the price of the house, approximate price of the house, would you say that it is beta 1? It will depend. Let us say that you are given data like this, x1, x2, which is the length, width, number of floors, x3, and the price, 1. So width, length, floors, and price. You get a spreadsheet of data like this. Now you're trying to predict the price in terms of these three variables. You may do that. There is you'll get certain degree of relationships plus beta 3 x3, but you would realize that actually there is another factor, which is the dominant factor. It is not the length and the width and the things. They do matter a little bit. But much more important is the product of these two. In fact, the product of all these three. Let me call it beta 4. What does this signify? Can somebody tell me? If I take the length of the house, the width of the house, and the number of floors, what do I get approximately?
The square footage?
Exactly. You will get the square footage. And you know that the price is actually sensitive to the square footage of the house. So for example, if you get a house which is only 900 square feet versus a house which is 4,000 square feet in the same neighborhood, which is likely to be what are you doing? You have to create that predictor. You are effectively creating a new feature by multiplying original features, right? By the product of, by multiplying some original features. Are we together, guys? And this sort of multiplication are called interaction terms. This is an old word that comes from the statistical literature. They refer to these terms as interaction terms, where one term, like width and length, interact and floors interact together to create a new important feature called the square footage. Do we understand the concept of interaction terms, guys? Anybody? Is this way? I hope this is simple.
Is the interaction terms calculated observations, or it comes with the data?
No, it comes with the data, and what you do is you create these terms by, so for example, here, you get this data, but you should keep in mind that sometimes more important than the original terms can be the interaction, the product of the terms, right? And you treat it as yet another variable. Right? You can literally think of it as x4, isn't it? You can define x4, which is square footage, as x1, x2, x2. Isn't it, guys? And so then you write the equation in terms of these things. In fact, x1 and x2 may not matter that much. You may keep them in the equation, but predominantly, the most important feature will become your x4 feature. This is just extending the linear model, the standard linear model, with interaction terms. Or that we previously saw we could add polynomial terms. Now they are interaction terms. It's very simple, guys. That's all there is to it. Huh? And in the code, it becomes very simple when you do interaction terms. Like as you will see today, we'll walk through the code for linear regression. Some simple examples. We'll do it in R and we'll do it in Python. And you will see the value. Perhaps today or perhaps tomorrow, next week, you'll see the interaction terms in effect. But this is the concept of an interaction term. So you should ask yourself, do I need to add? So this is a question to ask. Do I need to add interaction terms, right? Number one, right? Number two, a question that you have already asked, do I need to add polynomial terms? You realize that polynomial gets even more interesting because you can have, for example, x1 square, you can have x2 square, and you can have x1, x2 as an interaction, second order term, isn't it? And you can even have x1 square x2, you can have x1, x2 square, and so forth. You know, you can talk of so many polynomial terms that you can add. And now you begin to ask yourself that, well, that is a whole lot of questions to ask. How many terms should I add in this regression? The answer to that usually is you start with the simplest model. You see if that works, If it doesn't work, then gradually you complicate it, you experiment it. There are no sort of recipes on which approach to take, where to stop, and so forth. So this has been a problem in linear regression. In the simpler machine learning models like linear regression, it is a sort of, it comes with the territory that a lot of experimentations have to be done by hand to make it work. As we progress through the machine learning course, you will realize that there are much more powerful algorithms later on that you encounter where you don't need to do this, which are smart enough to figure it out. And magically, they sort of figure it out and they adapt to the data and they figure out what's going on. Right? They sort of know that they are what the real degree polynomials are and so forth. And we'll come to that later, but we are starting with just linear regression. Huh? This is it. Now, this is a limitation of linear regression, that you have to do these experimentations by hand. So far, so good, guys. Are we together so far?
Just on the one of the conditions for assumptions of this thing is the random thing. Can you a little bit elaborate on what is a random thing when you say?
Very simple. It just means that when you gather the data, make sure that it is a truly random sample of the reality. Like data shouldn't be biased or skewed. Let's say that you're supposed to find the height of children, right? Who are fifth graders, and the school has 100 fifth graders. A random sample would be that you take a sample of children, some are small, some are tall, etc. A non-random sample would be you find the tallest kids in the fifth grade and you bring them, and now you try to use that. Right? Because that second situation is not really random. It has a bias, isn't it?
Right. Okay.
So just avoid bias in data. It's common sense sort of a thing.
Thank you.
How can we find out the data is imbalanced?
See, you can never really do it. What you can do is you haven't seen the reality. Somebody has brought you the data in a business situation. You don't have the luxury, unfortunately, most of the time, to ask the question, is there bias in the data? Right? Or, no, you can ask that question actually. Is there bias in the data? And you can look at the input data and see what is going on. But suppose you look at the data and everybody's height seems to be 6 feet onwards. Just looking at the data, you wouldn't know that the data is biased. Very hard to tell. You need some external information. You need a domain expert who will tell you that you have just caught hold of some basketball players here. These are not normal people. It's a biased data. So bias is a systemic problem in machine learning. And avoiding bias, discovering bias is one of the crucial things. For example, I work in talent management. And when we do research, one of the fundamental things, and it is required by US law, that you have to ensure to the best extent possible that you are not discriminating based on, or there is no bias based on the protected classes. The protected classes being gender, race, age, disability, and so on and so forth. That your data does not have underlying bias so that you end up with results that is favorable to one versus the other. And do biases happen? Do they still remain? That is your worst nightmare, that in spite of your best effort, there may be a hidden bias in the data somewhere, right? That you will discover later on. It easily can happen.
And increasing the size of the data set gives advantage to find the bias?
Yes. So there are many ways of doing it. First is that, see, if you can control the experiment that produces the data, right? If you are not just a person who receives the data, but are on the ground, at the grassroots level, gathering the data in the field, then you can control for biases. The second thing is you can take a lot more data and hope that it is harder for more data to have bias. Are we together? So imagine that you just randomly pick 3 people. It is possible that those 3 people may all be very tall. But if you truly randomly pick 100 people, and the process was random, the probability that they all happen to come from the high end, the basketball range, is very, very low. So size of the data certainly helps you. Sometimes though, you don't have the luxury. See what happens and we will do a lot of these experiments. See those data sets that I asked you to analyze in the exploratory data analysis, we'll carry them forward throughout this workshop. We will do machine learning exercises on them. Right? So we will predict the California house prices. We'll predict, one of them is breast cancer. Actually, I haven't released that, but you'll do that. Predict whether somebody does or does not have breast cancer based on the predictors. Right? And you will encounter a lot of these data sets. Some of these data sets, people have tried a lot to remove bias, make sure there is no bias. Sometimes you can't avoid it. So if you receive data and you were not there producing it, you should go with the assumption that there may be bias. Are we together?
One more question is, assuming all the other conditions meet except the collinearity, let's say it's present, can I drop that particular parameter and go with the rest of the observation?
All you do is, and that is why you should first do exploratory data analysis, because if you do it, if you look at our notes, what is one of the first things we do? We find correlation, isn't it? Pair plots and correlations. So in the correlation matrix, it will immediately stand out that two predictors are highly correlated, isn't it? And the moment you find that, you know that linear models will go for a toss. So you pick one and ignore the other. You don't put both of them in the model. You pick one.
Okay.
That is exactly the way. And we will do not today's lab, but the next lab. Next week is all labs, guys. Huh? So we will walk through some lot of code to understand this. So that is what it is. Now, I must make a point that is important, guys. See, traditionally in the field of statistics, people did hypothesis testing and confirmatory analysis. Like they would start with data that they knew or were assured or had some confidence is unbiased. And then they would check whether a hypothesis is true or not. Right? The world that we live in is the world in which data comes at you. You don't get that much flexibility to control the experiment in a large number of situations. For example, you get Twitter feeds. You can't control what people are saying, writing, isn't it? You just get the data. You get vast amounts of data, but most of the data sort of emerges. It comes at you. You can pretty much try to grapple with it, and it's there. What you can't do is set up an experiment in many, many real life situations where you have ensured that bias is not there. So you are in a world in which the thing that becomes most important is exploratory data analysis. And that is what we have been doing in the first labs, the first notes that you got, lab notes. That is what it was doing. Today, exploratory data analysis in the world of big data is dominant. The confirmatory analysis is there still, the other half of statistics, but you don't get much opportunity for this in many, many real life situations. Sometimes you do, sometimes you're lucky you do. And that is a big shift in the field of data science, in machine learning. We are in a world in which you take data as it is, and you try to make predictions and build models and find patterns in it as it is. So, all right, guys, that is the Gauss-Markov assumptions. And remember that you should respect that. You should check whether data follows these assumptions or not. If it doesn't, then there's a word of caution. Your models may not be good models. And if I were to point out one thing that the many, many textbooks in machine learning fail to emphasize, it is this. And how do you systematically check in your data analysis that you are not being misled? And we'll do that in the labs. Right? Now, there are other things that can mislead it besides multi-collinearity and so forth. So let me talk about two more culprits or criminals in the space, you can think of it in the data. One is outliers. What are outliers? We all know what outliers are. So suppose you guys are all standing there, and what is the joke in India that Amitabh Bachchan comes by, and he's extremely tall actor. Right? So then he practically looks down on all of us. what would you call his height? When it is very different from the population height that is looking at him, you say that he's unusually tall, isn't it? The word unusual comes to your mind. Or out of ordinary. Out of ordinary comes out in your mind, isn't it? So if you plot people's height, most people's height, let's say, is there, or in your group will be, and then there will suddenly be this guy sitting like very, very tall, whose height is like this. What somebody sitting here is, or somebody sitting even far out, let's say we have a people's height like this, and this goes off to, and here is a guy, you are here somewhere, let's say that you are somewhat tall, but here is this guy who's very tall. What do you call him? You call him an outlier, right? Because he's outside the mass of, or the basic population of the data. Does the intuition make sense, guys? Or let's say that you get a very, very short person, and that person is an unusual dwarf, right? Let's say that you get a 2-foot human being, and that person is, let's say, 50 years old. Now you would say that, well, that's unusual. There are very, very few such people. Most of the people, their heights are, I don't know, between grown-up people have heights between 4 feet and let's say 6.5 feet or something like that. But occasionally you'll get a 7-footer, 7.5-footer, and you'll get a 2-footer or something like that. So they are unusual people in terms of the population with respect to height. So another question is, what's a more technical definition? In one dimension, outliers are easy to find. What people did is they all took, there's a guy who did the first exploratory data analysis book, I think, to my knowledge, Chukier. He's quoted in my notes, very influential. So he said that if you make the points which are one standard deviation away, one standard deviation is sigma, and this sigma, one standard deviation, this, right? And then you find things that are 2 standard deviations away here. So this is another sigma. So up to this, he said, are inline data. Yeah. So minus 2 sigma to 2 sigma, he called inline data. Inliners or liner, not linear, inliners. And outside the range, greater than 2 sigma, right? And less than minus 2 sigma, right? So here, this region, the next sigma that is here, next sigma, he called it the greater than 2 sigma, less than 3 sigma, right? Less than 3 sigma. This sort of data he called the soft outliers. Like they are outliers, and then things beyond plus minus 3 sigma, he called like strong outliers. Are we together? Does this make sense, guys? So I'll give you an example of what an outlier is in very practical terms. When I was in IIT, we had a particular class. The class was very hard. To make matters worse, the professor gave negative marking. And so most of our marks or grades we all scored somewhere around 0. Quite a few got negative marks, quite a few got like 6, 7, 8, or 9, or something like that. But in our class, there was one guy who absolutely loved that subject. He just wanted to do that subject. And guess what he got? He got 100 plus 100. So that would be an outlier. As simple as that. So guys, have I conveyed the notion of outlier simply? For one dimension, it is You just look at the standard deviations and you get a sense of the outliers. For higher dimensions, 2D and higher, it's a little bit more tricky. In 2D, you can still do that. So suppose you have data like this. Let me take data like this. Data is here. Any data set is here, let's say. And suppose there is a data here. What would you call this data? Do you notice that it stands out? The nearest neighbors are a little far off. This would be called an outlier in 2 dimensions, x1, x2. It is an outlier, maybe it is, yeah. Are we together, guys?
Can you, on the same 2-dimensional or 1-dimensional, can you give examples, real life examples of soft outliers?
Yeah, a soft outlier would be, see, a simple soft outlier is, let's go back to the beach. Suppose you're looking at the wind, the tides and how high the tides are. So suppose it's a pretty stormy day, what will happen? The tides will be quite strong, isn't it?
Yes.
That is an example of a soft outlier. The sea is responding to the winds. What would be a huge outlier? Something like a tsunami, right? Because tsunamis are unusually high, like 30, 40, 50 feet high or 100 feet high. Tidal wave. Any tidal wave that comes and hits you would be a strong outlier.
Strong outlier, yeah.
And it is very practical. In naval tradition, all the ships are designed to deal with soft outliers very well. But their big fear is, what if a strong outlier comes? What if a gigantic tsunami or tidal wave comes? Then all bets are off. Completely all bets are off. So that's an example of soft and hard outliers. So that is outliers. And then I'd like to finish this with one more concept. So outliers, they stand out. Good, lovely thing about outliers is they're easy to spot. So these criminals, you can, in the data, you can sort of spot, oh, there you are. Do you notice that you spotted the outlier just by doing a geometric visualization of the data? In higher dimensions also, there are techniques that you can do that. You can look at the distance to the nearest neighbor or some means. It gets more sophisticated. Outlier detection and anomaly detection actually becomes a very sophisticated field. Now, why is it important? In higher dimensions and in complicated situations, this whole business of outlier detection is important because, for example, crime. Most people, let's say, imagine that you have a network, and most of the people who log into your computer systems in your network, they have a fixed pattern. They log in, check their email, work, and this and that. So if you look at their behavior, they will all be inline data. I mean, in other words, their behavior will look like other people's behavior. But then comes a hacker, and his whole pattern of behavior, he'll hop from machine to machine to machine. In a quick succession, he would have gone and compromised like 30, 40 machines. That is unusual. A normal employee doesn't go and work on 40 machines in a day unless he's a system admin, isn't it? So there is a very anomalous behavior that will stand out as an outlier. And so this whole business of outlier detection is very vital. It's a core activity in machine learning. It's sort of a specialization in its own right. And entire companies make huge amounts of money. They have business based on just one specialization, ability to find anomalies and outliers in the data. Novelty is special. People use the word anomalies, outliers, novelty. I'll use the word somewhat synonymously. There's subtleties there in that. And detecting it is quite a game. It's a cat and mouse game, actually. And for medical, for example, many diseases, the lab test results will stand out as outliers. And we'll know that something very unusual is going on. So that is outliers. But there is another class of things which are slightly different. They are called points of high leverage. So high leverage points. Right? So high leverage points are like points which, for whatever reason that you can't tell, is sitting somewhere, hiding somewhere in the data. But if you remove this point, your model will change. It's very interesting. So suppose your model is like this, and if you remove this point, your model will become like this. Hypothetically, this is what happens. These are points of high leverage. And it is very specific to linear regression. When you solve the problem, it turns out that for whatever reason, these points are, when you just visualize the data, you can't see them. But they are sitting there and they hijack your modeling exercise. They make your models not as accurate in prediction. These are high leverage points. You can't see them. So now you need mathematical tools to do that. And those mathematical tools you'll see in the code. Let's do it by example. We'll actually do our data analysis and see it with that. Are we together, guys? So these are points of high leverage, and there's use mathematics to find them. Now, why do these things matter? The reason they matter is, look at this outlier. What is it doing? Without the outlier, your model would look like this, isn't it? Are we together? This blue line is what your model would look like if this outlier was not there. But because this outlier was there, it is tilting the model towards itself. It's making the model go like this. Does this make sense, guys? Because this is also pulling the line. Do we understand that? Just a few outliers can distort your model and make it much worse. So outliers and high leverage points, they spoil your linear models, and you have to watch out for them. When you build linear models, you have to check, were there any outliers? Do I need to remove them? Were there points of high leverage? Do I need to remove them? Right? So those are the questions you ask, right, in linear models. And this is, again, very specific to linear models. Watch out. Leverage points, high leverage points. High leverage points. But outliers have a very interesting behavior. See, this guy is an outlier, isn't it? But I can have another outlier here. And you realize that if these two outliers are there, they may effectively cancel each other out, and you may get a model like this. This yellow line, which is very close to the blue line. Are you seeing that, guys? The outliers on both sides of the fences, they may end up canceling each other out, the effect. And they may pull the data, the solution towards the line that would have been the solution if these outliers were not there. So outliers may or may not screw up your analysis, but certainly it's worth finding them. And generally, it's a good idea to see what happens when you remove them. High leverage points are actually much more dangerous. When they are present in the data, you're pretty much screwed. You know that your model will be impacted. The quality of your model will be impacted. There is no getting around it. And the moment you find points of high leverage, first thing you do is take them out. Are we together? And the word leverage is very apt for it. It's somewhat, if I have to give you an analogy, imagine that there is a decision-making body. And there is one guy, and whatever he says has unusual influence on all the decisions for whatever reason. What will happen? That person has unusual, you might as well just have that guy in the meeting room, isn't it? So one way to get a consensus, or you give everybody a voice, is to essentially take that guy out of the meeting. So that is the concept of high leverage. Are we together, guys? So we'll take
Just
this.
have a question.
Go ahead.
From an outlier perspective, do you think at any point outliers are useful? Like, why do we have to always remove them?
No, not only for linear models. Remember, I said that these are the problems that you worry about only in linear models. So linear models, like the linear regression model and logistic regression and so forth, we'll do later. Linear models have a lot of limitation. One of them is they get hijacked by outliers and leverage points. May get hijacked. Right? Leverage points certainly, outliers maybe. Right? So you'll have to treat it. Ask, should I remove it? What would the model look like if I remove the leverage point? I mean the outliers. But outliers in themselves are good things because sometimes you are in search of the outliers. That is the signal you're looking for. For example, a lot of fraud detection is simply based on that. Credit card fraud is a search for outliers in data. So let us say that you do most of your purchase in your hometown. Then all of a sudden you start buying Apple, a MacBook or an Apple Watch in, let us say, Oklahoma. That data, and you start buying a lot of fancy, expensive electronics there. That data should stand out as an outlier, because normal behavior is you stay in your hometown and any given day, you don't splurge on too many electronic items. You might buy an iWatch or you might buy one day an iPad, but on the same day, you don't go buy all of them.
Can the outlier kind of help us in also determining what the upper and lower bounds of our data, of our whatever we are looking at is?
Yeah, it is. It is possible. So, for example, if you are doing, I'll give you an example. If you're making a building, very simple example, you're making a building and you have the stress that the building will go through. You have data on the stress points, the vibrational data. Right? It is an industrial zone and you're looking at the vibrational effects. And the wind shakes the building and many other things. You don't want to structure the building, the structural strength cannot just depend on the normality conditions.
Right.
You have to factor in the earthquake, which will be an outlier data. So when in the data you see this suddenly massive stress, you can't say that, no, let's ignore that data point. I will build a model and predict, I will use the amount of steel. If I'm predicting how much steel and how strong the steel and concrete should be, I can't make the prediction. The strength of the building based purely on the inliner data and remove the occasional earthquakes, which are all sitting as outlier stress points. See that, right? So you can't always ignore outliers. You have to take the outliers into consideration.
Can we also say based on that if we encounter an outlier and based on our thought process, if we find that outlier to be important, we have to go away from a linear model, even though it makes sense?
Yes, certainly you have to do that. That is why the outlier treatment is very important, and we'll do that. Nisarg, as we move along in this workshop, we'll do that. As you know, in the boot camp, we have an entire day devoted just to outliers. Remember that. So we'll come to that in due course of time. So guys, at this point, I'll just recap what we have done, because I'm done with this thing. Multilinear regression and the univariate linear regression is a part of it. People often don't use the word multilinear, they just say linear regression. So do we know now what it is? Would it be fair to say that we now know what it is, guys? Let's review. Would you say that we know this?
Yes.
And what are the factors that affect it? So collinearity or multicollinearity, outliers, leverage points, they all affect it. What is multicollinearity? We saw when two predictors show, what do they show? What is multicollinearity? Who would like to phrase it for me?
Either increase or decrease.
Yeah, when two predictors are highly correlated.
Have
Or more basically.
dependence to the output.
Or another put it is, correlation between two predictors xi and xj is approximately 1, very close to 1. 0.9, 0.9 is close to 1, right? That is a sign of multicollinearity. What are outliers? Who would like to explain what outliers are, guys? Anybody?
They are the observations which lie outside the
Yes.
usual 3 sigma.
The other population of observations. In one dimension, soft outliers are beyond 2 standard deviations. Hard outliers or strong outliers are beyond 3 standard deviation. Right? In higher dimensions, it is that data point that stands away from other data points. Right? That's outliers.
When we say, when we use standard deviations here, Asif, we are assuming that it's a normally distributed.
No, you don't. You don't have to. That normality in the data is not necessary. It may show a Poinsot distribution or any other distribution. For example, suppose you have a distribution which is very common these days, like this, long tail, or like this. The definitions of outlier still remains. Beyond 3 sigma, it is outlier. Beyond 3 sigma, it's outlier. And in fact, the modern economy is based like, so the whole question is what is outlier in these distributions, right? It's a very interesting question. It turns out that there is a tremendous amount of data that is sitting there, and sometimes in long tail, you don't quite get an outlier because the tail is very heavy. It's a very interesting topic. Let's not get there. But at this moment, I will just say that it is not necessary for it to have a normal distribution. Normal distribution is an intuition. Are we together? But for example, this guy is an outlier. If you look at people's salaries, by the way, in a university, this is real data, by the way. I happen to have done this. This is how the compensation of employees in a company look like. But guess what the compensation of the executive staff looks like? It's out here. It's typically 1 or 2 extra zeros added to the normal employee's compensation. Right? So what would you call that executive salary? That is a classic example of outlier. There are very few people with that kind of salaries in the company, right? Compensations in the company.
Percent.
Yeah, 1 person or 2, 3 people, the executive staff. Right? So those are outliers together. That's what outliers are. What are points of high leverage, guys? Who would like to recap before we take a break?
Points which have an unusual effect on the model.
Yeah, exactly. They don't look obvious. They're hiding in there in the data, but they have unusual influence on the model. And so you have to use the right mathematical tools to discover them. And we'll see in the lab how you do that with data. And finally,
can we say that outliers will also be leverage points?
No, they're not. They never. Leverage points are always inliners. They're sitting hiding in the middle of the population. Are we together? They are in. Think of them as they are in disguise, sabotaging your model. They're saboteurs, looking normal and basically screwing up your models. Now, what are the? Who would like to tell me what are the 5 Gauss-Markov assumptions for using linear regression? Anybody would like to name them?
Random sampling of data.
Yeah, your sample should be truly random because you shouldn't have bias. What else? Anybody? Somebody else?
Linear equation.
Yeah, you should have a linear equation. Very good. Somebody else gives me the third one.
Homoscedasticity.
Yeah, it should have homoscedasticity. Means the variance of the error shouldn't change with the value of the target variable. That's right. Right. In other words, you should not have this cone shape. This sort of a cone shape that you see here, or when you plot it against the residues, this kind of residuals, they should not exhibit. The error shouldn't exhibit this cone-like structure. Right. The variance should remain constant. What other factors are there in Gauss-Markov assumption, guys?
Collinearity should be absent.
Collinearity should be absent. Excellent. Did we miss anything else?
No pattern in residuals, basically.
That is the homoscedasticity. The errors must be
normal.
Normal errors.
well curved. So that is great, guys. It's very interesting, actually. When people come to interview in my team, and usually I get a mix of people with masters, just aside, people with masters from good universities, and a lot of PhDs come. And people these days, they are very fixated on what is hot. So everybody would know what is there at the cutting edge of research, because everybody has attended the latest meetup meetings, meetups, and so on and so forth. But when I start interviewing people, I go back to the foundations just to see how well people understand the subject of machine learning. And it is quite depressing how few people actually know the field at all. They just practice the field. They don't know it. They know sort of by practice, a mechanics experience, but they don't have a good theoretical understanding of what exactly is this field doing. When can I use a linear model? Very simple question. Go to your place and ask somebody, when does linear models work? They will say when the data is linear. But it isn't just that. Linearity is only one of the criteria that needs to be met. So guys, I'll stop here. What I would like to do is, Prachi will give you guys a quiz. Take a break of 15 minutes. And in that break, let's make it 20 minutes. 20 minutes break. It's 8:40. We'll regroup at 9. Also take the quiz. Prachi, have you posted the quiz to Slack?
No, Asif, I'm just doing it right now.
Please post it to Slack. And guys, all of you, take a break, go drink water, get some dinner if you have to, meet your kids, come back, do take the quiz. It will give you a bunch of a basis of how much you have understood a reality check. Please take the quiz. With those words, I'll stop the recording. We'll take up the recording again when we, where am I? Are you guys seeing my screen here? I don't know where my recording thing went. Wait. Oh, yeah, here I know what happened.
Yes, yeah. I think you're still recording.
All right, guys. So in this iris data set, which is the simplest of all data sets, like I said, everybody starts more or less with iris in the career. We have a simple data set for regression. But at this moment, we are not doing regression, and we did exploratory analysis. We have 5 features. One is what is the species of the flower, and then the sepal length, sepal width, petal length, and petal width. Out of those 4 features, we do the exploratory analysis, and you can see all the code. It is there in your notes also, and here is the notebook, the HTML export of the notebook, the R Markdown. I've posted all of this, and the R Markdown and everything, so that you can use this code and do that. Now, likewise for weather dataset, I've done in both R and Python. All of these, this is your weather dataset. I've given out the solution. See, guys, if you haven't done the homework, I would highly recommend that at least you study the solution, give time to studying it, and gradually catching up and trying to do it, and study the notes. So this is for the weather data set, and this is in R. And then you can do the same weather data set in Python. And it looks not very different, the analysis in Python. As you look at this, you realize that it is practically the same. I hope you have read this in the notes. It is the weather data set. Now, the one data set that you haven't quite studied is the California housing data set. I asked you to do on your own. So here is the solution to that. I've done it here. So once again, you read the pandas data file for housing. You tabulate a few rows. This is just applying a good style to it to make it look pretty. Then you draw it on the map. So for map, there is a lovely library called Folium. Import that library, and with that library, you'll be able to project data into the map. What am I doing? I'm finding the center of California. Right? And then I'm making that the position of the map and zooming out from that. Zoom zoom level, then you get essentially a part of the map which is focused on California. And then a bit of color, a splash of color, and so on and so forth. So this is the data. You notice that just by looking at the data, let me see, what can you tell looking at this data? Can you make out the two population centers, guys, in California? So for people in California, this is pretty obvious. You can see the Los Angeles population center, metropolis. You can see the Bay Area metropolis here, where my mouse is. And you can see the Sacramento. And you can literally see the Central Valley and this Route 5. And you can see some population around that. I don't know, is this Route 5? I think so, I don't know. You can see some populations around that. So this is it. The data is housing data. This was collected in the 1990s, I believe 1995 or something like that, the house prices. So what I have done after that is I have projected this data onto just a scatter plot, as simple as the scatter plot of the points, longitude, latitude. And what do you see here? The darker the color, the more expensive the house. Clearly, the house, it is no surprise that metropolitan areas tend to have very expensive houses. They are also the bubble here, the size of the bubble gives you a sense of how much population is there. The more the population, the more the. Now, you notice that there is a lot of code that goes. This may look like a lot at this moment for you. You're creating a scatter plot, you're doing all this label, aesthetics, etc. So it is the nature of data visualization. Soon, the scatter plot or the scatter function of matplotlib will look very easy to you. It is just one liner. You start by just making a rough and ready graph. Then what you do? You try to improve the aesthetics of the graph. You notice that I've added some things which are not quite necessary. I've added a color map which says that what is the color gradient to use to show the salaries, the median house value, sorry. And then S is size of the bubbles in the scatter plot, alpha. This is transparency. There's a lot of data here, and it begins to look rather cluttered and hard to make head and tail out of. So one of the very common tricks that you use is you sort of make most of the data points only like very, very transparent, all the data points. They are only 20% opaque. So that at some point there has to be a lot of data for the color saturation to take place, which you see here. So you'll also see that I use some of the LaTeX syntax, not necessary for you to use, but generally to create production quality graphs. It is a common practice to insert LaTeX syntax. In my notes, I mentioned that. So this is it. If you don't use it, of course, don't use it. If you LaTeX has a very steep learning curve, but the rewards are really worth it. Here, by the way, I've just what I didn't show is that I've saved these two images, and then I wanted to put it in a notebook side by side in the lecture notes. So that is there. And now, what was I doing here, and why is it saying this? I don't know. What was I doing here? I will fix and repost it. I think something has happened here. So this we'll have to see. AW plot color is salmon. Oh, color. This is wrong. Yeah. Let's check on that. Data is not defined. Anyway, I need to go fix this code. I'll do that immediately. So then we look at, first thing we look in the data is that the ocean proximity has only 5 values. You're either near the ocean on an island or not near, or near the bay or inland. So those 5 values, you convert it into categorically, right, as type categories. And that is something we'll learn in the next lecture. Then you look at the data, you draw the normal histograms, then you make the pair plots. By now, pair plots, if you have been reading the notes, they should be pretty familiar to you. These are the pair plots you make. You can make category plots, pair plots and counts. How many data points, how many houses are on an island? Very few. How many houses are near the bay? Again, this is a concentration of houses near the ocean. Lots of houses in California are near the ocean. Inland, a lot of things are here, and many houses are within an hour of the ocean. There are two plots which are very informative. One of them is called the violin plot. They give you a sense of where most of the data is, at what value. Like, for example, you notice that where the bulge is, where the height is, that's where the data is. Most of the data points are concentrated. And it gives you a nice smooth representation of that. So if you're looking at median age of the house, from this, you can pretty much see that houses that are near the ocean, they tend not to be more than 50 years old. But houses on the island can be 60, 70 years old. So can anybody name the island in California?
Catalina Island.
Catalina?
Yeah, of course. Yes, very good. So there we go. So this is it. And this is the box plot that gives you the standard deviation, the 2 sigma deviations, and then the outliers that you see here mentioned. So these are box plots. You are all familiar with box plots. What I've done here is shown all the box plot, 9 box plots in a grid. And try to make it, see, when you make graphs, it is important not just to make the graph, but to make it aesthetically pleasing. I haven't done too much effort, but a little bit, because then if you make too much effort, the code becomes a long, complicated code. This, with very limited effort, do you notice that this graph looks very, I would say, fairly presentable? You can put it in your document, in your report, and so forth. To the extent that in machine learning, a lot of the work that you do is complete mystery to people in the business side. You have to tell a story, and your graphs help tell a story. Now, you may wonder that how did I produce those lovely tables in the document? So one of the, and this I just kept it as an illustration. One of the lovely things that Pandas has is that you can convert any data frame into LaTeX. It will emit it out as a beautiful LaTeX table. Now, those of you who know LaTeX would love to see this, right? Because it is terrible to key this in by hand. And of course, if you don't know LaTeX, just ignore this one. The correlation matrix, so you can see all the correlations. You'll find notes about what you can observe. For example, house median age is highly correlated with population, with total number of rooms, and so forth. Right? So in other words, the older homes used to be bigger homes. Now, as the concentration, as the population gets more and more dense, there seems to be a tendency to have less big homes. Smaller homes are more popular. And then after a little while, we'll go into more stuff. We will do machine learning on this. For example, we learned regression. So the next thing I would invite you to do, and it's a bit early, but remember, we'll do it one day. Suppose I ask you, based on all these features, can you predict the house price? Longitude, latitude, median age of the house, total rooms, bedrooms, population, etc., and proximity to the sea. These are all factors. Can you predict the median house value? By the way, data here is at the level of 1 block. So if you see a huge number of rooms in a house, it is not a house. Each data point represents an entire city block. So the goal here is to predict what would be the price. And Zillow does that, right? And all this Trulia and all of these things do that. So we will do a similar exercise based on these features. We'll try to predict the house price and see how accurately we can do that. It's a very real world example. This data is a little bit old, but it's a fun thing to do. We'll do it in due course of time. But I highly encourage you that as a warm up to that, you do go and do this exploratory analysis so that when we are doing that analysis of machine learning, we only focus on the machine learning part, not on the exploratory analysis part. Together. So, all right, I won't do. And by the way, these maps, do you notice that I can zoom in, zoom out? These are live maps. This is the beauty of Folium, right? Which is based on leaflet. And the R equivalent of this is literally called leaflet. So that is that. I won't go into it. And then what are the weather data set? Once again, I've given you both versions of the data. So here is the data in R, the notebook. And here is and I posted it all to the discussion group. And here is the same notebook, but now in Python. You would realize that not much difference. Both these languages look, the notebooks in both the languages look almost identical. One reason why you should learn both the languages, why not? And joins and so forth. So I won't walk through it because we have explained this in the notes. What I would like to do today is focus on the linear regression. So this is your next lab. I'm going to post it now, as a Google share in a little bit. So you guys will all get it. So linear regression and friends. And here I define linear regression as with polynomial terms and with interaction terms and all of that. Right? But we'll start slow. Are you guys all able to? Okay, now I need to share this. Sorry, I haven't. I'm talking with not sharing. Let me share the other screen. Application. What application share? Let me know, guys, if you can see my screen. Can we all see this?
Yeah.
And so in this, let me make this even smaller. This is, we'll do linear regression with 5 very simple data sets. I created these because I've deliberately created this to illustrate the various aspects of linear regression analysis. Right? So we will do this, follow it up with real world examples like California housing and so forth. Are we together? So let me see, let's do it. And is this clear enough, guys? Or is it too small on your screen? Is it looking clear enough?
Yes,
It is clear.
Okay, yeah. So one of the things that I like to highlight is it's a truism in the field, and I think it broadly applies to all of science itself. People often say which is the correct model. When you build a machine learning model or hypothesis, the question often comes, now which hypothesis is correct? Now in machine learning, there is no such thing as correct hypothesis, or in science in general, there is no such thing as correct hypothesis. The only thing is, you don't know, the data is there. The forces that produce the data, the generative forces, you don't see it. If you could see it, there was no point in doing machine learning on it anymore. You have to infer it, you have to approximate it. The whole goal is to approximate whatever produced the data. So the question is, how good is the approximation? Is it effective? Is it useful? That's the only question you ask in machine learning. And George Box was a great, what we would call a statistician and a data scientist today. He said, he's made major contributions to this field, one of the great giants in the field. And his statement stands there to always remind us that all models are wrong. Whatever hypothesis you build is probably wrong, but some are useful. Means just because it is not the generative force doesn't mean that you can't use it. So long as it is a close enough approximation, it is useful. It makes good predictions, and therefore it is useful. So the measure of modeling, of machine learning, is the model metrics, the accuracy, the prediction error, how close it is, and so on and so forth. So we measure by that. We don't ask the question, is it the correct model? The correct model is the simplest effective model. That's sort of the Occam's razor principle. Given data, if you can build a very simple but very effective model, then that you can sort of define as the correct model if you want. It's called the Occam's razor principle. So these things, by the way, guys, in the lab, and I offer these hours, I encourage you to use it. If you haven't started using R Studio, or Python Jupyter notebooks and you are a bit hesitant, by this time there are a lot of people who haven't started. And I highly encourage you to come to these extra sessions that I offer in the evenings, where I'll walk you through the setup, where I'll make sure that on your machines, these things work. Are we together? We'll do WebEx sessions and I'll guide you through. And there are TAs here who will guide you through the whole process. So use these facilities. So not much I'll say about here. By now, you know that this is it. This is splitting the data and so forth. You'll get to read it. But we'll look at the first data. So here is the journey that you'd go through when you do data analysis. First, you do exploratory data analysis. Here, I've made it very quick because we have to get into the machine learning part. So start with the EDA, all that we did in the first lab, and then come to this. So what do we do in the EDA part? We load the data, we investigate the data, we summarize, visualize the data, we see how it looks. So here we go. We look at the summary of the data and we plot the data. Are you guys seeing this plot of the data? Where my I don't know. Does this mouse let you? Yeah. Do you see where my mouse is moving, guys?
Yes.
So when you look at this data, it's a one-dimensional, like it's a single variable. X and Y is the prediction. What can you say? Do you think it's a linear relationship? A straight line is a good approximation? What would you say, guys?
Yes, straight line is a good approximation.
It is a good approximation, right? So let us see whether that hypothesis works out. So the syntax in R and in Python both is very, very simple. Look at this. You need to, and this is the beauty of it. I can't think of any other framework where things are so simple. In machine learning, you don't write a ton of code. Usually one-liners are very, very powerful. So the only code here are these two lines. You see what I've highlighted? Two lines. The rest is the output of the code. So the first line says, build a linear model, right? Actually, LM, I'm told, it doesn't stand for linear model. It stands for, well, it stands for the name of the two people who created it. I won't go into it. Levenberg Market and so forth. Market. So it says that Y depends on X. You see this tilde here? It says Y depends on X in this line of syntax. And what it is saying is build a model where Y depends on X, a linear model, and save it in a variable called the model. And then the summary is a general purpose function in R. When you say summary on anything, like here we say summary on the data, it will give you a summary of the data. If you say summary on a model, it will tell you all the parts of the model, the beta naught, beta 1, and so on and so forth of the model. So when you look at this, the first thing that you start with is actually here at the bottom. Does the, and by the way, there is look at these two things, multiple R squared and adjusted R squared. Today, in our modern world, just ignore all of these different subtleties. We'll come to it, I'll explain it someday, but just look at the adjusted R squared as the R squared that we talked about in our lectures. What is the R squared about? What part of the data can be explained by your model, right? TSS minus RSS over TSS, remember, total error. Null hypothesis error minus the error of your model divided by the null hypothesis error. If you go back to the notes, you'll see it in the previous lectures. So good R squared, and R squared goes from 1, which is very good, and then goes down to 0 and can even become negative, unfortunately. So it means your model can be even worse than the null hypothesis. You can be totally misguided if it gets negative. So here, big R squared is good or bad? Anybody?
It's good.
It's good, right? It's good. The bigger the R squared is a good. But one thing about regression and anything is, no one measure you can trust and say, all right, it's a good model. Right? You have to look at many aspects of it and then tell. It's very much like a physician. When you go and meet your physician or family practitioner, He doesn't just take your temperature and declare you to be in perfect health. He or she will also take your, blood pressure, will look up your throat and do many other tests. Look at your blood test results. And if everything is normal, then she will declare you to be healthy. Otherwise, if any one thing is wrong, then what happens? If, for example, everything is normal, but the blood pressure is high, will your physician declare you to be normal? She wouldn't. She would say, we have a problem. And the same applies to the output here. This output that you get, you have to look at many aspects of it, and all aspects of it have to be good. So I'll just cover what those aspects are. The R square has to be good, which seems very good. Then let's look at this part. We are now going to focus on this part, right? What it says is the intercept, the coefficient of the intercept. In our language, it is the beta naught, isn't it? When we write the equation, y is equal to beta naught plus beta 1 x, this is beta naught, right? This 3.45. And let us see, look at the data and see if it makes sense. What is the intercept? It is the height y at x is equal to 0. Does this look to be about 3? Give or take. It does look to be 3.5, isn't it? Let's look here. This is where it meets, right? So it does look right. This is it. Now, the beta 1 seems to be this. Slope seems to be about a 2.7. So let's approximate it 2. So what it means is that if you increase by 10 units, the y should have increased by how much? Approximately 21 or 22 units. Right? Let's see if that is true. At this value, is y approximately 21, 22? Right? 22 plus 3.5, right? Because the intercept is 3. So 25. Is it approximately 25? It seems to me. Right? Does your model agree with the data, guys? Are you able to interpret it? See, if the slope is 2.7, slope is what? The increase of y with respect to x. So if x increases by 10 units, y should have increased by approximately 20 units, actually 22 units. And then the intercept is 3, so 25. Y should be around 25. 25 is here. Let's go here and see. Is that what you get as at x is equal to 10? It seems to be, right? Along the x-axis. X is 10. Right? Maybe the fonts are very small. You're not able to see it. Let me zoom in huge in this and see one page at a time. Single page. Let us go maybe. Hold on. Is this picture more visible, guys, now? Even more. If you look at this picture, can you see that at x is equal to 10, y is approximately equal to 25? Anybody would like to confirm that?
Yes.
And you would agree with that. No? So this value that the model is predicting makes sense. Now, what is the standard error? Standard error is the like how sure you are about this, like taking different samples. What is the value of beta naught and beta 1 that seems to emerge from the data? I'll give you an intuition of standard error. Huh? So let us say that you go to open grocery. What is that? Farmers market. And there are two farmers. One of them is selling you apples for let us say $5 for 10 pounds. Right? That seems like a pretty good deal, perhaps 50 cents a pound. So you say, well, I'll take it. But he says, the bags are approximate. It may be 10 pounds plus minus 5 pounds. Right? Then the other farmer says, no, my apples are $11 or not $5 a pound for 10-pound bag. Mine is actually $6 for a 10-pound bag. But it will be 10 pound plus minus half a pound. It can be somewhere between 9.5 pounds and 10.5 pounds. So which farmer would you feel like buying your apples from? The guy who's selling for $5 or the farmer who's selling you for $6? Make a guess and justify that.
The $6 one.
And why would you do that?
Because the chance of the error is very close to what we're paying for.
Yeah, so you're much more sure what is it that you're paying for. Whereas with the $5 guy, you might end up with just a £5 bag instead of a 10-pound bag. Or on the other hand, if you're really lucky, you might end up with a 15-pound bag. Though knowing shops, it is unlikely to be true. Right? So you might end up getting shortchanged. So you prefer more precise answers. There's always an error bar. There's always a margin within which the value falls. And this is the measure of the margin. So when you see a value 3.45 and it says plus minus 0.24, does that look to you fairly reasonable? It's not bad. It could be 3.6, it could be 3.2, or isn't it, at most? All of these look pretty good estimates of the intercept. Likewise, for slope, it's even better. It's 2.17 plus minus 0.4. Well, that looks pretty good. Right? That would be considered good. So the t-value is actually the ratio of the value divided by standard error, sorry. So if you look at the 3.45, when you divide it by 0.24, 0.24 is approximately 1/4, which means you're multiplying 3.45 by 4. Well, let's take a 3.5, that will come to approximately 15. So you see this t-value is 14.28. It's just the ratio of these two. Do you see that, guys?
Yes.
And this one is 2.17 divided by 0.04. The t-value is 53. So this is for people who can't take ratios, etc. See, this results that you are seeing here is it's a celebrated result in many, many fields. People have used these tools for many, many years in social sciences and in psychology, in many fields, in economics and of course science, the stronger sciences, medical sciences and STEM, the hard sciences, physical sciences, and so forth. So everywhere, and what you are seeing is, or being acquainted with, is something that you will find this result quoted like this in many, many journals and papers and articles, and people, your company will show results that will look like this. That is why I'm explaining it out to you. So,
Asif?
yes.
So why are those good results? The intercept NX. How can you say that those are good results?
See, this is the thing. It is a way to judge. It is literally when a value has error bars which are very close. Means you have a good, you compare all of these together. You have a good R square. You're getting values and the error bars around it are pretty small. So you look at the t-value. This is literally the 2. Generally, t-values of, in my experience, a rule of thumb, above 5 is pretty good. Right? So somebody gives you a 5 apples and says plus minus 1. You say, all right, I'll take it. Isn't it? Well, somebody else may have a stronger standard. It depends on the context. See, in scientific journals, physical sciences, physics or chemistry, physics, for example, people want the error bar to be very, very small before they accept a new theory. But in some fields, let's say in psychology, data is by definition mushy, it's soft. Human beings are not so easy to quantify behaviors. So you tolerate a much wider error bar. So it's a judgment call. What is the t-value that you'll accept? Generally, I would say that anything below 5 or 4.5 is really not good. A good ones would start at, let's say, 10. And if you're looking at a very significant research that will have a lot of impact, your t-value should be quite big. Error bar should be quite small. And then comes a thing which I will teach you, but I hope you'll forget after that. It is called the p-value. It is something that has unfortunately been abused a lot. What is the p-value? The word for that is statistical significance, is the name. Statistical significance. What this says is it is 2 into 10 to the minus 16. It's a scientific notation. 2 into 10 to the minus 16. So is that a big number or a small number?
Close to zero. Small number.
Very small.
Very small.
What is this p-value? Roughly speaking, it is the probability that your model is actually fooled by data. Null hypothesis is true. What is the null hypothesis? There is no relationship between x and y. Together. And that's the null hypothesis. If the null hypothesis is true, then your p-value will be very high. Probably, obviously, 1 means 100% sure that the null hypothesis is true. But if the likelihood that the null hypothesis is still true in view of this data is very, very low, what does it mean? It doesn't mean that your model is the best model, but all it means is you might be on the right track. Are we together? You might be on the right track. Now, this p-value has become notorious because for many, many years, people used to think that a 5% p-value, like if your probability that the null hypothesis is true is below 5%, you would feel pretty good. You would feel that, okay, you are seeing some relationship between the predictor and the response. And so that is where this convention comes from. If your p-value is very small, like less than a 1,000th of a percent, and like 0.1%, then for people in different fields who have a bit difficulty interpreting it, what they do is they just look at the stars here. They see 3 stars, say, oh, great, I found a predictor that really seems to matter. If it is 2 star, it means that p-value is 1%. There's 1% chance it may still be wrong. And a single star is 5%. If they see a single star, it means it's around 5% or less. A lot of fields say it is perfectly fine. Then a dot means maybe, it is 10% chance that your hypothesis is, the null hypothesis is true. And if it is just a space, there are no stars, it means that quite likely your null hypothesis is true. Yeah. And you don't really have a model. Are we together, guys? It's a way to interpret how good, how much each of the predictors matters. Right? So as an example, I'll take, if you're selling ice cream on the beach, then the temperature matters, the wind speed matters, but probably how many penguins jumped off Antarctica into the sea on that day doesn't matter. Right? So its p-value will be very high. Right? It would not matter, basically. Right? Those, or whatever estimates you come up with would be just bogus. Are we clear, guys? Right. So here the p-value is this. Does this look to be good or bad?
Good.
Good.
That should be good, huh? 10 to the minus 16 is practically 0. It means that you're probably looking at a good model. Now, what has happened is the p-value has been abused. In many, many fields, the R squared can be quite small, like 10%, 12%, 15%. And the thing is, data has a lot of noise in it. It's very soft. How do you judge whether a certain predictor does or does not matter, is significant or not? And people have always looked at the p-value more and more, and any p-value less than 5%, and they will say, oh, we have got even worse than that. People would like rig their experiment in such a way to somehow achieve a p-value less than 5% so that they could publish their results. They could write a research paper. And when we look in hindsight, we realize it's a disaster. There's a very entertaining book. It's called The Cult of Statistical Significance, which basically deconstructs all the bad things. I mean, it basically says all the bad things that can happen if you just get fixated on p-value. P-value is still a good measure, but it's one of the measures. Don't just trust it. And some people believe that it's a useless measure. But let's give it some credence. It's there. The frequentialist, it turns out that the machine learning crowd is divided into 2 camps. the frequentialists and the Bayesians. And the frequentialists like p-value still. The Bayesians are very distrustful of the p-value. So for what it is worth, it is there. So when we look at this model, is there anything alarming that you see? Anything that makes you believe this is not a good model? The F statistics is related to p-value. It is a measure of how good your model is. We'll just leave it in that. And degrees of freedom, etc., I'll talk about later maybe. We have 99 points. We have beta naught, beta 1, 2 parameters. And basically, if you subtract 2 from 99, you'll get 97, right? The free degrees of freedom. It needs a little bit of an interpretation, but it's really not worth going in now. We'll go in later when we have a bit more maturity. But so here, the adjusted R square looks good. Think of it like a patient's temperature. Or, oh, this looks good and this BP, etc. Everything looks good. There's nothing alarming here. So from that, you may think it is a good model, but it is not enough. One more thing we need to do is we need to plot the residuals. Remember our Gauss-Markov assumptions? One of the things it says, what does it say? We must establish that all those assumptions are met by a model. Linearity is simple. Data, obviously, we have taken the data and we know what it is. But the one thing that we need to know is this. Hang on, where am I gone? That is important is, see, when you plot the residuals along the model, the y hat, right, or the y, doesn't matter, then what should you see in the residuals? They should be uniformly spread, right? Homoscedasticity. You should not see the spread, more spreading, the errors spreading out in one direction or the other, more than at different places of y. Simply put, what it means is you shouldn't see a distinct pattern in the residues. When you look at these residues, do you see a pattern, guys?
No.
No. So this is just take it as a fact. Absence of pattern in residues is good. As you scan your eyes from left to right, you should not see a significant change in the structure of the residue as you move your eyes from left to right.
Just one question. So the pattern that you're mentioning, what you said as you scan your eyes left to right, that means if that was a straight line, your residual data should not be aligned to that line. Because to me, it looks like there is a pattern. So could you kind of clarify what you mean by not a pattern?
The data point, so here's the thing. Suppose along this point, let's say -10, around this region, residuals were mostly in a very tight band. They were, let us say that they were between -1 and +1. Are we together? So they were all here. These points didn't exist. These points which are far off didn't exist. Here, residuals were just between -1 and +1, right? But on this side, they're between -4 and +4. So you distinctly see a behavior, right? That here, residuals are not so spread out. Here, residuals would be much more spread out. Are we getting that? But if you look at this, residuals seem to be equally spread out everywhere. In other words, the variance of the residuals does not change based on the value of y hat actually here. They seem equally spread out in both as you move on the left as well as the right. Did you get it, Irfan? I think you asked.
No, I got it, because when I originally saw this, when you said there was no pattern, all I saw was the circular data on the left, and then I thought there was a pattern, but that's fine. I get it. So you're basically saying it should not be dense, essentially, to show that there is no.
That's
okay.
It shouldn't be very, dense in one place and blown out in the other end. You shouldn't see a funnel-like effect. Right? So far so good. Our residuals look good. It doesn't still mean that we have a perfectly good model. There is one more test you should do. You should plot your predictions on the data. See what the data is saying and what your predictions are saying. So there is a bit of code, R code, and usually it's very interesting. You see that the machine learning code was much easier We did the machine learning in one line, 2 lines. Where is it? Let me go up. You did the machine learning here in just 2 lines, right? But when you try to visualize the code, plotting code, it tends to be a little bit longer. Here, we are plotting the model on the data. Like we are taking the predictions of the model and we are going to plot it on the data. Then you have to write a few more lines of code. It is actually very easy code, but you need to get used to the plotting library of R and Python and so forth. And which is why you should start early, guys. Those of you who haven't started doing your homeworks, it's high time you started on it, because you have to practice these things. These things have to gradually become second nature. And these things essentially cannot be done. It is a lot of it is just monkey see, monkey do, and read the documentation, the API, the plotting API, and do it. Look at examples and do it, and that's all it is. In other words, there is not big theoretical depth to it. You just see, understand, and do. How do I learn about any new plotting library? I just read a lot of examples, then go read the API, figure it out, and then do it. And then it happens, I forget it. Then I go back and look at examples, look at the API, and get it back. That's it. So now here, the maroon line is the prediction, and the blue and the green are the upper and lower bounds of the prediction. Remember, I talked about the standard error. So they are this like the upper bound and the lower bound of that. So when you look at the maroon line, do you think it is a good representation of the data, guys?
Yes.
Yes, it does look like it. So this is a good thing. At the end of it, when you reach this stage, then you feel that, all right, we do have a good model. So what all things we did? We loaded the data, we did exploratory data analysis, we summarized and visualized the data. Then we built a model. We looked at the model diagnostics. They looked good. But we didn't get satisfied with that because that itself can mislead you. We looked at the residuals to see no pattern there. There was no heteroscedasticity. That looked good. Then we moved on to finally making the predictions and plotting it on the data. And even that looks good. So this is good. Now, in your career, you won't get many situations where you build the first model and it succeeds. So enjoy it. Like when you're looking at this exercise and you do it, enjoy it while you can, because most of the time, life is more complicated. Right? And we will see complications in our very second analysis. So this is where everything works the first go itself. Real life is more complicated. Any questions?
I have a quick question. I saw something like a confidence interval in the last the error chart.
Yeah.
Is that on the right side? Yeah.
So basically, what it says is, hang on, let me make this confidence interval. Let me explain to you visually what it means. Where is the plot in the next page? See, when you look at it, right, it says that with 95 or 99% confidence, you can be sure that your prediction is between the blue and the green. So suppose this band is narrow. It means that you have it doesn't matter whether you pick the blue line or the maroon line or the green line. They all seem to be good. Maroon is slightly better than both blue and green, but they're tight. But when the lines are far apart, means you don't know with confidence what the actual value is for a given x. I'll give you a real example. Once I was dealing with a rather complicated problem, and I built a linear model. I built not a linear model actually, a complicated model. It was different. I was doing it in Spark, and it was big data, and it had taken hours and hours to run. Next morning, it finally finished. When it finished, we were overjoyed that the model has finished. And we asked it to make a prediction. It predicted a value. I don't remember what the value is. Let's take the value 7 for something regression. Then we asked, okay, what is the with 95% confidence? What can you say? It is between what and what? And the answer came out to be, it is somewhere between minus infinity to plus infinity. Right? So would you trust that model?
No.
No.
Right? Because the confidence into the 95% confidence bar is way too wide. Right? I mean, you give up at that moment. You realize that you haven't succeeded. You have to try again, build a different model. But here the two lines are very close to each other, so it's a good thing.
Okay.
Asif, in the same figure, I see the green and the blue lines moving farther apart from the maroon at the edges, but they are very close at the center. Is there anything that we can understand at this point, or it's
yes? Let me. What happens is when you are near the center, right? In the neighborhood, there are far more data points, isn't it? Opposed to here, look at the edges. Literally on one side there are no points. So data becomes what you call sparse. Less data is there on the edges. Right? When there is less data, your confidence goes down. When there is a lot of data, you make more, more robust or more confident predictions. That is why these lines are closer to each other. It's very nice that you observed. Who is it? Who observed?
Asif, this is Balaji. And I mean, like I was about to say, it's a standard error related to the lower and upper bound.
Yes, they are quite related. Though this is the confidence interval of the model itself. Right? The prediction.
I see.
So think of it like that. It is related, is derived from that, basically. Right? And the formula is very simple. It literally starts with standard error. The analysis of the data set, 2. So if you look at by the way, where are these data sets, guys? Anybody can tell me, where is this data set? All this
GitHub.
In the GitHub. And the GitHub link is there where? In your notes that you already have, guys. Huh? So you all have that. If anybody doesn't have, please reach out to us, post the question in Slack and so forth. And one of you, actually Aprachi or Dennis, one of you, could you please post the link to the GitHub on the Slack once again? Just as a reminder.
Okay.
The ML100. So you see all the data. So this is the second data set. I won't go into loading the data. It's the same code. But when you summarize the data, it's a surprise. Look at this data, figure 1.3. Looking at the figure, would you say that a straight line is a faithful representation of it? Yes or no? All right. In fact, this seems to have two bends, right? So certainly a straight line shouldn't work. And this is the interesting thing, guys. See, in 2 dimensions, you can see it. There's only one predictor you can visualize and see it. Unfortunately, in real life, the data sets come with very high dimensionality these days. Right? Forget high dimensionality. Even if there are 4 predictors, you can't visualize data in 5-dimensional space. Right? So sometimes it is not obvious that the data is nonlinear, that you don't have a linear situation. So how do you proceed? When you can visualize in 1 dimension, is great. When not, then I will help you understand how you can do it. Once again, we do the same exercise. Do you notice that? Same code, we build a linear model and we look at it. We say y depends on x. So what are we trying to fit here? We are trying to fit a straight line to the data, right? And here is the danger of it. Suppose you had not visualized the data. Look at this model. You get an adjusted R square of 60%. 60% is considered pretty good, right? You have a pretty good model here. Does the p-value look good, guys? I see 3 stars. So to me, it looks good, isn't it?
Yes.
The t-value also seems to be pretty good. Actually, they call it t-value, but in the book, you'll see it called t-statistic. T-statistic also looks good.
But only one of them. The other one is not good.
No, it's good, right? 10 and 12. Only the size matters.
This, I see.
Not the sign of it. So this looks pretty good, robust. So
the error is so much, right, sir? The standard error is... Oh, that will be also plus minus, right?
That's right, plus minus, yeah. That is it. So actually, it's a limit. It's just a limitation of the tool. I think they should just have looked at the size divided by the size and remove the sign, because quite a few people ask the same question that you ask. It's confusing. So, guys, if you look at this, in many fields, an R square of even 23% is considered very good, right? Because data is soft. You look at 60%, you may feel pretty good about yourself. You look at all the other metrics, they seem to be good. In fact, they seem to be even better. P-value, the notorious P-value seems to be so good, isn't it? But here is the surprise, and this is why I feel that most of the textbooks, they just stop here and it is wrong. When you visualize the residuals, what do you see now? Do you see a pattern in the residual?
Yes.
There is a distinct pattern in the residual, right? And so when you see a pattern in the residual, you know that you have left signal on the table. You haven't captured the complexity of the data because pattern is information, right? You haven't aligned yourself. If you had squeezed the juice out of it, the residuals would be just random noise. You know, when you squeeze the juice out of lemon, there is no juice left in the lemon. In the same way, residuals should not have information in them. But here it looks pretty distinctly to have patterns. And it shows up when you put the prediction line on the data. Look at this. Do you see the maroon line? It is the best, if you think about it, it is the best straight line that you can draw through the data, isn't it?
Yes.
Would you agree? Except that straight line is not the solution. Right? Which is why it is important always to look at residuals and try to visualize the data on the predictions, because you will know that you may be barking up the wrong tree. There is a scope. It's not that the previous model is wrong, but there is a huge scope for improvement. Are we together?
Yes.
So now let us go and try to improve upon this model.
Sir, one question. So when we applied linear model, right? So there was intercept has almost 10% of standard error, right? If we see so, and that tells something because 10% is more, right? If we go up a little bit.
Depends on the situation. See, what happens is that a t-value, I said above 5, right? People begin to feel it's reasonably good. So both of the t statistic, which is the ratio of the estimate over standard error. See, look at this. This is 1.27 plus minus 0.1. Many people will consider that pretty good.
I see.
Also, these are pretty good values. But R square is 60. See, looking at this, you can't tell that something may be wrong with the model, which is why I say most of these textbooks that you find with code in them, they do you a disservice. You have to go the extra length. You have to check for residual patterns. You have to plot your predictions over the data and see how it works. So how would you go about it, guys? You notice that this curve has how many bends?
Two bends.
So what degree of polynomial do we need to solve this? Remember, I talked about it in the past.
3.
3 degree, a minimum third degree polynomial, right? Minimum. So let's do that. Let's try to fit a third degree polynomial to it. And let's see what happens. This time, well, the code is not very different, actually. It's surprisingly the same. Look at this code. What did I do? Instead of y just depending on x, I'm saying y is a third polynomial of x. And guys, do you see the expressive power of these libraries? Can you imagine doing something so powerful in just one line in any other framework? Right? You are doing pretty powerful machine learning exercises with just one line of code. These things mean real things, in real life, in business. You end up with results quickly and you can talk about it. It means something in the real world. So now we do that. We have a third degree polynomial, pretty good. Let's look at the R squared. Is the R squared better? Remember the previous R squared was 60%. Now the R squared has gone to 96%, 97% approximately. Is it better or worse?
Better.
It is better.
Right? It is close to perfection, it seems to. But there is something very interesting. The intercept doesn't seem to matter. You notice that the intercept, the p-value is bad, the t statistics is bad. Right? The first degree, beta 1 is fine, beta naught seems to be pretty bad, beta 1 seems to be good, beta 2, second degree polynomial, the second part of it, quadratic term seems to be bad, the t-value, t statistics is bad and the p-value is bad, but the third term is also good. Right? So, when that means, it means that probably you don't need the first and the third term. The first and the, the intercept you don't need, and you don't need this thing. So, you can iterate over it. You can go back and build a model only in X, this part, the beta 1 and beta 3, right? This term, the third degree term, and try it out. And when you do that, you may want to throw in X5 also. If you do go to the fifth term, you realize that X4 doesn't matter, X5 matters, and so forth. So it takes a certain degree of experimentation and playing around till you get better and better models. There is no end to how much you can improve. But remember, there's a thing called overfitting. Too good a model is also bad, and we'll come to it in a later time. Now, one of the things I'm doing here, and it's very important, I have not split the data into test and training data. I'm using all of data to basically build a model. When you build a model with all the data, you have a problem. What is the problem? You don't know whether you have overfit. You have very high variance errors. And so we should have split the data 70-30, 80-20, or something like that. But because it's our very first exercise in machine learning, I have removed all complications and in a way deliberately kept it over simple so we can get to the gist of the matter. We learn the machine learning part first, and then we worry about the nuances. This is it. So this model, what is the next thing we'll do? We'll do a residual analysis, isn't it? So let's look at the residuals. Look at the residuals. Here are the residuals. Looking at the residuals, guys, let me zoom in even more. When you look at the residuals, do you see a pattern? As you go from left to right, your eyes go right.
No.
Not very visible pattern. It's a significantly better. Like look at this situation, figure 1.6, and compare it to, let's see, this one, figure 1.4. Figure 1.6 is a sea change compared to figure 1.4, isn't it? Would you agree, guys? This one distinctly shows a pattern, a straight line model, and this one is a much better improvement. Most of the pattern has disappeared, isn't it? If not all. Would you agree with that, guys?
Yes.
So it is giving us a hint that, so far so good. We might be heading into a good model. And finally, what is the last step? We need to visualize the predictions on the data. Let us do that. And now look at the maroon, the predictions. Do you think this is a good, like it is a good model for the data?
Yes.
Yes, it is. It is indeed, right? And see, the lesson to learn here is don't just look at R squared or just p-value or one of these things. Remember, there can still be scope for improvement. One clear way to see that there is scope for improvement is look at the residuals. If they show a pattern, means there is a scope for improvement. Also, plot out your predictions. See if they agree with the data. If they don't, then you don't have a good model. Huh? So there are many ways you can go wrong. And you'll never know whether it's correct or not, because there is no correct, but you have a good approximation if you pass all the tests.
So on the data with on the legend, the data has the black line. That you mean the data points?
Yeah, because the black are the data points, yes. The circles are the data points. The black circles are the data points. Maroon is the prediction, and the blue and the green are the upper and the lower bounds of the prediction. So far, so good, guys. Anybody has a question or needs explanation?
Asif, a trivial question. From the previous graph, I see where the points are dense, that's where the confidence is moving apart here. Quite opposite to my...
Yes, it is not. Because there is a bend. A bend needs a lot of information, and it is not bent enough. So how much should the bend be? Should it rise more? Should it be a more like a less steep bend? Right? So the steepness of the bend is not quite uncertain through the data. If you really look at it, you can see it. Right? I could have moved, for example, I could we consider that maybe the right answer is between the maroon and the yellow, maroon and the green, isn't it? So it's a little
better to be more precise. Like that's how the confidence. I mean, I'm trying to intuitively go at it, but yeah, there might be more mathematics.
that is like how confidently in that region can you tell the exact. So by now, guys, you must be feeling that polynomial is the real trick, right? Let's use polynomial regression. And the history of this field is that, as I said, Gauss first used it in a published paper in 1793. Right? So remember that if machine learning is a new subject, remember that. Then 1805, Legendre wrote the famous paper. We use the term least squares, principle, method of least squares for regression. Then obviously, he didn't use the word regression. Later on, Pearson created the word regression, Galton and Pearson, and so forth. But the interesting thing is, people already latched on to polynomial regression early on in the early 1800s. They started doing it, and they were quite successful in many, many situations. But then let's look at dataset 3. Are you guys able to see dataset 3? Once again, summarize and plot it. Well, how many bends do you have in this data? I see a bend here, but there's certainly a bend here and a bend here. Maybe a bend here also. So minimum 4 bends, right? 3 bends, let's say. So you would probably start with a modeling with degree 4. Does that make sense? Isn't it that? Now, in this example, if you try to model naive a straight line model, you will get a disaster. Do this exercise, guys. That's how you develop intuition into data and machine learning. So you do the same code. By now, this code must be looking very familiar to you. You take the model and you summarize it. And then you look at the adjusted R squared. What does it say?
7%.
Very low.
0.7. It is just a disaster, right? Already it's a disaster. What about p-value? The only thing you can be reasonably sure of is the intercept. And there is no slope to this line. You can't be sure. And even the estimates are close to 0. So when the slope is 0, means what? Y doesn't really depend on x. Y is just beta naught, isn't it? Because beta 1 is approximately 0. What is another name for such a situation?
Null hypothesis.
Null hypothesis, isn't it? And that is why you see the p-value is 18, 19%. It's a disaster. Suppose you're not alarmed by that enough. Let's see what the residual looks like. This is the residual. What can you see about the residual? Do you see a pattern in the residual? Right?
Yes.
You see that, practically see the original curve sitting there, which means that the line captured nothing. Your model captured nothing. Most of the signal is still lying there on the table, isn't it? So let's move past. Suppose you insist on blindly using your model. Look at your model and look at the data. Would you, in your right mind, consider this to be a usable model in practice? This much
No.
time? Anybody?
No, sir.
It's a disaster, right? In every way, in 3 ways, we know it's a disaster. The model metrics say it's a disaster. The residuals say it's a disaster. And the predictions say, when you plot the predictions on the data, it says it's a disaster. So what can you do? You say, well, we already know the trick of polynomials. Let us use that trick. Let us whip up a degree polynomial. So you can try degrees of 2, 3, 4, right? But you see at least 3 bends, so you should probably start with 4. When you do it, you will realize, and you can keep on experimenting. Surprisingly, you'll realize that you need to go to degree 7 before you get a reasonably good model. Some people get it at 6. I don't know. It depends on that. And at this value, what is the adjusted R square, guys?
94%.
94%.
4%. That looks good, isn't it? Do the t statistics look good in terms of values? Looks good. This one looks a little bit worrisome. The first order term, it's only 5.5. Remember, in size, it should be greater than 5 would be a nice thing. But you see this lovely array of 3 stars, isn't it?
Sir.
So just looking at this data, you would say, well, this is a good model, isn't it? Right? But you should not be satisfied by that. You move past it, and what is the next thing you need to do?
Residual.
Right.
And you look at the residual plots, and what do you see? So you see a pattern. It is much less pattern than before. This model seems to have done a better job, but still there is pattern there. Right? So it's a little bit disappointing. Right? So you say, well, you know what? And not only that, do you see that here, the error bar, like the variance of the error is low here. And here the variance of the error is high. The error spread out. Do you see that? Guys? I want all of you to notice that here errors are spread out this far on this right hand side. On the left hand side, errors are very tightly located. Do you see this, guys?
Yep.
Yeah.
Yes.
So what is the name for this kind of disease?
Heteroscedasticity.
Heteroscedasticity. That is right. So you also see pronounced heteroscedasticity. Literally, you know that even though it's quite a surprise, isn't it? You look at the model statistics and all looks well. Right? You look at this and you say, lovely, I'm going to market with it. And then you look at this and you realize that there is pattern there, there's heteroscedasticity there. And then you plot your predictions on the model, and what do you notice? You notice something. Actually, I wish I had those legends were up there because I wanted to show you. What happens is in the center of the data, it looks good, isn't it? This curve looks good. But around the periphery, what do you see here? And what do you see here? You see these oscillations. Do you see the oscillations on the periphery, on the left and the right? Right?
Yes.
So those peripheries are a disappointment because what it is doing is sort of trying to overfit to the data. And there is a name for that, actually, those oscillations. It was discovered by a great mathematician called Runge. And yeah, and yes, it is named after him. It is called the Runge phenomenon. So what it means actually is this. When you see the Runge phenomena, it shows up when you try to model a data with a very high degree polynomial. Are we together? So with low degree polynomial, your model was not good. With high degree polynomial, it seems to give good metrics, but it tends to develop these oscillations. I actually give it a more figurative name. I call it the wagging tail. I have a dog and my dog's tail wags. So I call it the wagging tail because it reminds me of my dog. Its scientific name is the Runge phenomenon. And Runge discovered it a long, long time ago. And that's when people knew that polynomial regression has its limit. So how do we tame this? How do we go and tame this? So there are many ways of doing it. One is to realize that polynomial regression may not be the best tool to deal with it. And in the very next lab, we'll deal with it with a better tool, which won't show the Runge phenomenon. The other is we can do something called regularization. There is specifically an antidote. You can think to this particular disease, there's a Runge phenomenon. It's called regularization. And regularization is a pretty important topic in machine learning. We will cover it later in this workshop. Are we together, guys? So this is it, right? That was Runge phenomenon. Then if you do dataset 4, you realize how many bends there are? One. So what should you do? You can model it with a quadratic equation, isn't it? And quadratic equation will work, actually. If you take a polynomial, polynomial degree 2 quadratic equation, it works with 99% R squared and everything looks beautiful. Nothing wrong with it. If you plot the residuals, even the residuals look good. The spread of the residuals as you go, it looks more or less. Data gets more sparse here, but that's the nature of the data itself. Right. Let us plot the prediction on the data. The model prediction on the data looks good or bad?
Very good.
Good.
Now here I wanted to illustrate another point that sometimes you can make this model and you can say that, can I make a simpler model?
This is a quadratic equation. If you remember, any quadratic equation, if you sit at the center of it, at the base of it, you can represent it with just the x squared term. You don't need the order x term. You don't need the intercept. You don't need anything. You just need the x squared term. Right? It is just a mathematical curiosity. And in fact, one of the things that I'm using this to introduce, this is a very simple example, probably doesn't call for it, but I wanted to use this very simple example to discuss a lovely bit of mathematics called the Box-Cox transform or the power transform. It asks this question that, let us say that we write a linear equation. How do we know whether it is y or y square or y cube that is a function of beta naught, beta 1, etc.? Or is it, suppose it is square root of y. Square root of y would mean it is a polynomial of degree 2, because then you'll have to square it on this side, and then here you'll develop square terms. So what is this? And there is a very interesting history, and I'll tell you the story the way I was told about it. So Box, the great mathematician, whose quote is there at the beginning of this chapter, he and yet another great mathematician called Cox. It so happened that they were brother-in-laws. One had married the sister of the other. One was in England, right? And the other was in, well, I believe Wisconsin or something like that. So one fine day, Sir Cox visited Mr. Box, Professor Box. And what do you do? They apparently, so the story goes, they went out hunting. Well, mathematicians make terrible hunters because they keep talking all the way. And nothing will be there. And anyway, it's winter, you don't find much. So they weren't doing much. And so they were talking. And along the way, they joked that, see, our names sound familiar. What if we create a paper? We wrote a paper with something interesting. Then everybody will be talking of the Box-Cox result. Right? So what started out apparently as a joke or a discussion actually amounted to one very significant tool for machine learning. It is called the power transform or the Box-Cox transform. It asks this question, what is the real relationship between y and x? Is it quadratic, cubic? Is it log of y as a function of x? What is it? Okay? So we will use this Box-Cox transform. I wanted this opportunity to introduce you to it. We will find what is the real relation. Now, Box-Cox transform works only with positive data. So we'll have to throw negative data out and then play with it. So when you do that, it says that, see, in this equation, y to the power lambda is equal to beta naught plus beta 1x. Where does it achieve a maxima, guys? Approximately at?
0.5.
0.5. So what does it say? It says that the square root of y is a function of beta naught plus beta 1x in this equation. So y is a function of what? X squared terms, isn't it? So that is a way to confirm, when you have data that you can't visualize, you can't see the curve right away in higher dimensions, but then it helps to do the Box-Cox transform, which is what I've explained here. And I just took this opportunity to introduce Box-Cox because it's a very useful tool that you should use. And you don't really find it in most books. Another way to do that, to know that you need a Box-Cox transform is, if you take a frequency plot or a histogram of just the target variable y, does it look symmetrical or does it look skewed? This blue thing.
Skewed.
It does look significantly skewed, right? It is right skewed. But when you take the square root of it, what does it do to that? What is the square root like? It is much more symmetrical, isn't it? Not quite symmetrical, but not absolutely symmetrical, but certainly more symmetric. Would you agree that the maroon is more symmetric and blue is more skewed, right skewed? And so the statement geometrically is the right relationship of y to predictors is that relationship, that function of y or transform of y that makes it into a sort of a symmetric or semi-symmetric distribution of frequency plot. There's a bit of mathematics and thinking around it, but I thought I'll tell you. It's one of the things most people forget to do. They forget to make a plot of the frequency plot of the target variable just to see whether they should proceed as it is or they need a power transform in the data. Together. And so I'm more or less done. So you do that, and with that, you get a fairly good model even with that. I won't go into the rest of it. You can read this. Now we go to the last data set, which is actually what happens if the data has almost no noise or zero noise, and you do the residual analysis, and then what happens? Well, something peculiar happens. So here is this data. Right? You plot it. What is the first thing you notice in this data? There seems to be almost no noise, isn't it? It's a nice smooth curve. Whatever function y is of x, this data looks extraordinarily clean data. Would you agree, guys? You don't see data points scattered all along the line. They are all sitting in a nice orderly march. So you try to build, and this is sort of a warning here. If you try to build a model, well, how many bends are there? How many bends do you see, guys?
One.
Well, one here, maybe one here, two. But when you try to model it, you'll realize that you'll get a reasonably good model at 4. At 2, you don't get a good model. And you wonder what is going on. Right? So look at 4, you got a fairly good model, right? Adjusted R square is 99. Oh boy, it's pretty good model. Would you agree, guys? Just looking at the model diagnostic, would you be impressed? Anyone?
Yes.
It looks very impressive, isn't it? But then you try to look at the residual plot. Oh, I haven't done the residual plot. Actually, I should have. The residual plot is will be misleading, and it's something to know that when the data is very clean, you get strange residual plots. Those residual plots do tell you that your approach is wrong. But sometimes you can ignore the residual plot because ultimately, if you look at the prediction on the model, the predictions of the model and therefore the model curve, it is not that far from the data. Perhaps for practical purposes, it is quite usable. Would you say it's usable, guys?
Yes.
It's pretty usable, right? And so even though there are strong patterns in the residuals, right, it can be quite usable. It's a lesson. But the fundamental problem is, why did it not work? Data was so clean. Why did polynomial regression not work? Would somebody like to guess an answer? This is the last data set for today, and we have 8 minutes.
Non-reducible error.
No. Any other answer?
Overfitting.
Overfitting, no. Anyone else? I hope everybody hasn't gone to sleep.
Non-real observation. How to say that?
So I'll tell you what it is. Guys, in mathematics, a function, there are 2 kinds of functions. Things that can be represented as polynomials of finite degree, let's say here the 4th degree, and there are a class of functions which actually cannot be ever represented as a polynomial. If you try to represent it as a polynomial, it will be an infinite series. Are we together? It will be a polynomial of infinite degrees. These functions are called transcendental functions. In other words, transcendental functions. It turns out that you would say that, gosh, why do we need transcendental functions? Actually, transcendental functions are one of the most magic things in the universe. Everything, most of what is beautiful around you and the laws of nature are written with transcendental functions. Very interesting. For example, the ripples that you see when you throw a pebble into a pond, you see ripples, isn't it? What are those ripples? They are sine and cosine waves, right? They propagate as sinusoidal waves. What is sine wave? It's actually a transcendental function. If you expand sine wave in Taylor expansion, it is an infinite series. X minus x cube over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial and so forth. It keeps on going, doesn't stop. It cannot be represented as a polynomial. Now, you realize when you throw a pebble into the water, close to the pebble, like close to the center, the height of the ripple is high, but far off, the height of the ripple is less, isn't it? You remember that? Believe it or not, that also is given by how the height varies from the center is given by a transcendental function. And I invite you to find out what it is. I'm just creating a situation to investigate. You play the drum, you know, your musical instrument, you play a drum. The vibrations of the drum are a transcendental function. You know, in an atom, you have the orbital structure, electron clouds buzzing around the nucleus. And it turns out that they are also spherical Bessel's function, a sort of transcendental functions. They're different modes of a transcendental function. They're literally vibrations of sorts of a transcendental functions. It's very, very beautiful. You know, those of you who remember your chemistry, remember SPDF. Do you remember the SPDF in the orbital structure of the atom? Well, most of you have forgotten. They are actually transcendental functions. And transcendental functions are everywhere. And then, so therefore, much of the data that you see around you, there's a transcendental function behind it as the real force producing it quite often. And so you need technology to capture that complexity, to capture the transcendent, to be able to deal with it. And obviously, it is a good thing. Otherwise, machine learning would have ended in the 18th century with polynomial regression. Isn't it? I'm joking, of course. But imagine that if polynomial could do everything, then you didn't need it. All you had to do is create a polynomial machine and it could do all regression, which it can't. And so the fifth data set is just to give you guys an example of that. And there is a bit of historic note, you know, you learned regression for quite some time. Almost 3-4 lectures we have been talking about regression. And there's a bit of history about where all of this comes from. You guys can read. And that is it. These notes, I'll post, share it with all of you guys. And do read the notes, do the lab. I will give lab hours again, along with the TAs. Reach out to them. They will help you. Reach out to me. I will find time. And I'll give some official lab hours, right? Clinic hours, for people to walk in and do the labs. With that, I will stop. Our next lecture will start with, guess what? What will we do in our next lecture?
Classification.
We'll go to the next machine learning algorithm, which is classification. And one thing, guys, I need to be able to find. All right. Where is the meeting? All right. Can I stop the recording, guys?
Yes.
So,
Yes.